Okay, in this video, we're going to look at how to evaluate this integral here. We've already done integration of that line integral along C1, C2, and C3. We're now going to look at how to evaluate it along C4, which is a circle mod Z is equal to 1. So C4 is traversed in the counterclockwise direction. So let's have a look here. Now, as we've already hinted before, we always recommend making a sketch of the situation. So we have we're integrating from I to -1 along this circle. This is the circle. So mod Z equals to 1 is a circle centered at the origin with radius 1. Since we are doing this in the counterclockwise direction, that means the segment of the circle we're interested in is this one here. So that is our C4. Now, mod Z equals to 1 is the same as R equals to 1, because mod Z is equal to R. Whenever we have a problem involving circle, it is always recommended to transform into polar coordinates. So since x is r cos theta and r is 1, so we are going to have x is cosine theta and y is sine theta. Along the vertical axis, this angle is pi on 2, so strictly radians this time for these calculations. And along the horizontal axis where -1 is, theta is pi. So that means in terms of integration limits, we're going to go from pi on 2 to pi. We are going to need dx, which is going to be minus sine theta, d theta, dy is going to be cosine theta, d theta. So then if we rewrite this in terms of the new parameter theta, so we've got 2x minus 2iy dx plus I dy. So 2x is going to be 2 cosine theta, it's going to be 2i sine theta, dx is minus sine theta d theta plus I cosine theta d theta. We are integrating from theta is pi on 2 to theta is equal to pi. Okay, right now I'm just going to work this out in terms of these trigonometric functions. I'm later going to show you a route we could take using Euler's formula, which is going to be much more convenient. So I just factored out 2 there. If I factor out d theta, I'm going to have I cosine theta minus sine theta d theta there. Okay, so at this point there is another route which I'm going to show you. but for now let's just proceed as this thing appears. So if we multiply out, the cosines are going to give us I cosine squared theta. The sines are going to give us I sine squared theta. Then the combined terms, so we are going to have minus sine theta cosine theta. If we multiply this one and this one, and then we multiply these two, that's going to give us plus sine theta cosine theta. Then you can see that these terms are cancelling out, and then these ones have got I common, so we can write this as integral from pi on 2. Oh, there's a 2 that we have missed. Okay, so this is going to be integral of 2I cosine squared theta plus sine squared theta d theta plus, but cosine squared theta plus sine squared theta d theta is 1, so this is just 2I d theta. So this is going to be 2I theta evaluated between pi on 2 and pi, going to be 2I into pi minus pi on 2 is going to be 2I times pi on 2, and this is going to be pi I. So that is going to be the value of the integral along the circular contour. Now I mentioned there is another route of evaluating this, so I'm just going to show you that now. So if we start, so let's say alternatively, so if we start with that pi on 2 to pi 2 into cosine theta minus, I think it is, minus I sine theta, and then this side we've got I cosine theta minus sine theta d theta. Okay, so according to Euler's formula, cos theta plus I sine theta is e to the I theta. So cos theta minus I sine theta here is simply e to the minus I theta. So this is convenient here if you are in complex plane, because instead of dealing with two functions, we're only going to deal with one function. Then here we know that in the in Euler's formula, the I is always multiplying the sine, but here the I is multiplying the cosine. So we are going to factorize. If you factorize the I, then we're going to have cosine theta here minus sine theta over I, but 1 over I is negative I, so we can write this as I cosine theta plus I sine theta. If you remove brackets here, we recover that. However, this is just e to the I theta, so pi over 2 So this is 2I e to the negative e to the I theta d theta. This times this is just 1. So that's going to be integral of 2I d theta as before. Okay, but a third alternatively, okay, even before we get to this point here, we can handle this here, because this is dz. So as soon as you have got x is sine theta and y is cosine, x is cosine theta and y is sine theta, then this is telling us that this is cosine theta plus I sine theta. So it's saying that z is simply e to the I theta. So dz, simply the derivative of this, the only variable here is theta, so we differentiate that with respect to theta. So that's going to be I e to the I theta d theta. So that's going to be dz. So that's something that we've had to find the long way here, because at the end of the day here we ended up with e I theta d theta, but that's simply dz. So we could have actually plugged that in here right away. Okay, so that's enough explanation there. So bottom line, integral of 2x plus 2iy along that circle contour is equal to pi I. So let's summarize. So in summary, okay, the integral from I to -1 of 2x minus 2iy dz is equal to, I think it was 4i along C1. Let's just check it out. So along C1, yeah, it was 4i. Then along C2, I think it was 2i. And then along C3, it was 8/3 I. And then along C4, it's pi I. Okay, so it's 4i, 2i along C2, 8/3 I along C3, and finally pi I along C4. Okay, so we're going to end this video here. So, but this is just example 1. In the next few videos, we're going to look at example number 2. So this was just example number 1.